Today we're going to talk about Rolle's theorem and the mean value theorem for derivatives. So first we're just going to do a quick statement of what Rolle's theorem is, and then we'll go through a pretty quick and easy proof. And then after a while, we'll take a look at the mean value theorem. So Rolle's theorem states that if you have a function f that is continuous on the closed interval from a to b, that is also differentiable on the open interval from a to b, and also that the value f of a is equal to f of b, then it is guaranteed that the derivative of f at some c value must equal 0, or at least some number c on the open interval from a to b. In other words, what this is saying is if you have a continuous differentiable function and the height of the starting and ending values of the interval are the same, there has to be at least one critical value on that interval. So there's a couple different cases we could look at. And the first is that the function f of x just equals f of a, which is equal to f of b for all of the values on a to b. In other words, this is just a constant function, right? It's just a horizontal line. And if that were the case, then the derivative would equal 0 at every single place on this interval from a to b. So you can just say f prime of x equals 0 for every c in the interval from a to b. Okay. So that proves it when it's just a constant function. And the only other case is that the function must not equal f of a or f of b, so the same, or at least one value c in a to b. So effectively, what this is saying is that if we have a function that goes from a to b, and we start at the same value that we end, and not all the values are the same, in order to get from a to b, I must have either gone up, like I did in this case, or gone down, like I did in this case in blue. And then in order to get back to my starting height, I would have had to add a maximum or a minimum to get back up to that value. And so now I think visually this is pretty clear, but we could say that the extreme value theorem guarantees an absolute max and an absolute min on any closed interval for a continuous function. And since this function is a continuous function, as we stated up at the top, f of x is continuous on a to b, that means we know there's an absolute max and we know there's an absolute min. And, well, fairly clearly, if we have our absolute max somewhere up here that is not the same value as f of a or f of b, we must have at an interval, in fact, every single interval, let's call this c here, for our first case here, where we've got up to a maximum, we know that f of x is going to be less than f of c for all of the values on a to b, right, except at c. And so that pretty much guarantees that we've got that absolute maximum there. And if we have an absolute max, that means our function must have increased. That would tell us that f of x is increasing on, we'll use the brackets here just for the college board sake, we're increasing on a to c, and we must be decreasing on c to b, or at least on some interval surrounding c. So we could have gone up to this and back down and back up, but we're just taking the most basic case. So we could have said some open interval surrounding c. And that would tell us that if our function goes from increasing to decreasing and it's differentiable, there must be a place where f prime find is equal to 0. So I think that's a pretty straightforward little proof of it. We can be guaranteed that we have a critical value somewhere on that. So let's just take a basic function, f of x equals 4x squared minus 20x plus 29, and see if it satisfies the hypotheses of Rolle's theorem on the interval 1 to 4. And then we'll find all real numbers C on the interval 1 to 4 that satisfy the conclusion of Rolle's theorem. Probably try not to spell things wrong here. So first off, we know that f of x is continuous on the interval 1 to 4 because it's a polynomial. And we know that all polynomials are continuous for all real numbers, and thus 1 to 4 must be continuous as well. We also know that f of x is differentiable on the open interval 1 to 4 for the exact same reason, because it's a polynomial. And third, we can find f of 1. F of 1 is 4 minus 20 plus 29, which looks like that's 13. And we can also find f of 4, which would be 4 times 16, or 64, minus 80 plus 29, which 64 minus 80 is also negative 14. Sorry, negative 16. And add 29 to that, and we get 13. So we've also satisfied the condition that f of A needs to equal f of B, which guarantees us, by Rolle's theorem, that there must be a critical value, or a place where f prime of C is equal to 0 on the interval from 1 to 4. So by Rolle's theorem, f prime of C equals 0 somewhere on the open interval from 1 to 4. And we should very easily be able to find what that is. We can just find f prime of x, which is 8x minus 20, set that equal to 0. We get x equals 20 over 8, or if we just divide those both by 4 from the top and the bottom, we get 5/2 or 2.5, which is clearly on the interval 1 to 4. And that's really all there is to Rolle's theorem. Right? Show that the function is continuous, show that the function is differentiable on the open interval, and then show that f of A equals f of B, and then you can just go through your regular methods to find what that critical value is. So the next theorem we're going to talk about is called the mean value theorem for derivatives. And it's got the first two conditions, the hypotheses of the mean value theorem have to be the same as what Rolle's theorem was. That f of x is continuous on the closed interval from A to B and differentiable on the open interval from A to B. And it says if that's true, then there must be at least one point in the interval A to B where the instantaneous rate of change is equal to the average rate of change on the closed interval A to B. So effectively, what's that saying? It's saying that the slope of the tangent line at some C value that's on the interval from A to B must be equal to the slope of the secant line that connects the endpoints of the interval. So over here in the picture, you can see in red, I've got the secant line that goes through x equals -2 and x equals 0. And we have found the slope, or we found the location of the tangent line that's on that interval between -2 and 0 that has the exact same slope as that secant line does. And that's what's guaranteed. The instantaneous rate of change, f prime, must equal the average rate of change on that interval. So let's go through a little proof of the mean value theorem before we do a couple of problems. So first off, let's assume that we've got a function that satisfies the conditions of the mean value theorem. And then let's write out the equation of what the secant line might look like through the points at A and at B. So we'll call the function f of x. That's just convenient. And that would tell us that the point at A would be the point A f of A. And the point at B would be the point B f of B. And so from there, we'll just go in and say, well, the slope is f of b minus f of a over b minus a. And using point slope form, we end up with y minus, we'll just choose, that doesn't really matter, but we'll choose to use point A, f of a. So y minus f of a equals our slope, f of b minus f of a over b minus a, times x minus a. And to turn this into a slightly easier form to look at, in fact, to turn it into just y equals, let's just add the f of a over. So we'll end up with y equals f of b minus f of a. And I'm sure we can actually see that there's a minus sign between there. Over b minus a times x minus a plus that f of a value. And so now we've got some function here, right? It's just a linear equation that represents the secant line through the points a f of a and b f of b. And what we're going to do is we are going to come up with some new function. We're just going to name some new function. And I'm going to call it capital F of x, just to kind of keep in line with our regular function notation. We're going to call it capital F of x. And we're going to say that capital F of x is equal to a function that represents the exact vertical distance between our original function, f of x, and its secant line somewhere on this interval. Well, how do we find a vertical distance between two functions or between 2 points? Well, we take one of them and we subtract the other one from it, right? Like we want to know the vertical distance between y equals 2 and y equals 5, we do 5 minus 2. Well, if we want to know the vertical distance between f of x and this secant line, just take one and subtract the other one from it. So that's what we're going to start off with here. And we can note that it's possible, depending on what our function looks like, that this secant line is above our function or that this secant line is below our function. So it's good to note that this distance could be a positive or a negative value, or capital F of x is going to end up being either a positive or a negative value or function. So we'll take our original function, f of x, and we will then subtract this whole big other function. So f of x minus f of b minus f of a over b minus a times x minus a plus f of a. And we're now just going to start looking at this function representing that vertical distance. And what we're actually going to do is we're going to utilize Rolle's theorem here for just a second, and we're going to see if this function satisfies all 3 conditions of Rolle's theorem. And we'll kind of do a nice little easy thing here at the end if it does. And it does. So first off, the function has to be continuous. Well, we said that f of x was a continuous function. And this function, our secant line, well, it's a line, so it must be continuous for all real numbers. And if you take a continuous function and subtract another continuous function from it, you get another continuous function. So this must be continuous on a to b. And we stated that f of x satisfied the conditions of Rolle's theorem. So the mean value theorem. And so we know that it's differentiable on the open interval from a to b, and any line is also differentiable from a to b. So this already meets the first 2 conditions of Rolle's theorem. So we know that capital F is continuous on a to b, as well as differentiable on the open interval a to b, because it is a difference of continuous differentiable functions. A line and function we said was continuous and differentiable on a to b. So the only thing that's left is to show that f of a is equal to of b, capital F of a is equal to capital F of b. So we're going to need a new page for this. So we're going to rewrite our function. Capital F of x was equal to f of x minus the whole quantity f of b minus f of a over b minus a times x minus a plus f of a. And so if we go in and we try to evaluate what is capital F of a, well, that just means we're going to replace all the x's with a's. So we end up with f of a minus, now this whole thing, f of b minus f of a over b minus a times, well, if x is equal to a minus a is 0, then we have a plus f of a here. So effectively, that just eliminates all of this, and it just leaves us with f of capital F of a is equal to little f of a minus little f of a, which is 0. All right. Well, then let's go in and see what happens when we look for capital F of b. Well, that will give us little f of b minus the quantity little f of b minus little f of a over b minus a times, well, now since x is b, this becomes b minus a, and then plus f of a. And let's take a look at what happens there. Well, this b minus a in the denominator ought to cancel with this b minus a up here in the numerator. So we're then just left with f of b minus, and I guess we'll just distribute this minus sign through everything. So minus the f of b, and then minus the minus f of a will make for a plus f of a. And then minus the plus f of a will make for a minus f of a. And we can see that f of b minus f of b is 0, and f of a minus f of a is 0, and this comes out to be 0. And well, since 0 equals 0, that tells us that capital F of b is equal to capital F of a. Therefore, we've now met all 3 of the conditions that need to be met for Rolle's theorem. So we can now go in and say that the conclusion of Rolle's theorem must be true. So that's going to guarantee us that capital F prime of c is equal to 0 for some c in the open interval a to b. Well, what was capital F? Let's go back and write out capital F again. Capital F of x was equal to little f of x minus f of b minus f of a over b minus a times x minus a plus f of a. Well, what's capital F prime of x then? Well, what's the derivative of little f of x? It's just f prime of x. And then we end up with this is equal to, well, the derivative of a linear function. That's all this is right here. This is just a linear function. What's the derivative of a linear function? It's just its slope. So we end up with f prime of x minus the slope of this linear function, which is f of b minus f of a over b minus a. Right? Remembering, I'm going to write this back up here. This whole thing here, this is linear. Right? So now we think back, what did Rolle's theorem tell us? It tells us that this derivative must equal 0, which tells us that this whole thing over here, f prime of x minus f of b minus f of a over b minus a must equal 0, which tells us that for our original function, f prime of, well, we need to replace this with a c, right? If this is a c, then this becomes a c. It tells us that f prime of c must equal, add this slope over to the other side, f of b minus f of a over b minus a. And it'd probably be better if I go in here and the way I should have from the start written these out as now c is inside of here because we've set this equal to 0. So f prime of c, capital F prime of c is little f prime of c minus that slope, giving us our result that we said for the mean value theorem. And that's our little proof of the mean value theorem. So if we have a function that's continuous on a closed interval and differentiable on an open interval, it guarantees us that it is going to have a place where the instantaneous rate of change equals the average rate of change. So let's just real quickly go through and use this on a couple little problems. So first, let's determine if f of x equals x squared satisfies the hypotheses of the mean value theorem on 0 to 2. So first off, we know that f is continuous on the interval 0 to 2. And we also know that it's differentiable on the interval 0 to 2 because it's a polynomial. And that's going to be good enough for the explanation for this one, right? All polynomials are continuous and differentiable on all intervals. So we are guaranteed by the MVT that f prime of c equals 0 on the open interval 0 to 2, which tells us that, well, we know what f prime of x is. F prime of x equals 2x. So we're guaranteed that we can then, I wrote out the Rolle's theorem. We're guaranteed that f prime of c is not equal to 0. I don't know why I was thinking we were still doing Rolle's theorem here. It's equal to f of b minus f of a over b minus a on the interval 0 to 2. So f prime of x equals 2x. So that tells us that 2x, or, well, f prime of c would then be 2c, must equal the average rate of change on this interval, which means we need to find f of b minus f of a over b minus a. And f of 2 is 4. F of 0 is 0. And if we do 2 minus 0, that's going to be a 2. We end up getting 2c equals 2, or c equals 1, which tells us that c equals 1 is the singular value that satisfies the conclusion of the mean value theorem for x squared on 0 to 2. It's the place where the average rate of change is equal to the instantaneous rate of change. And so, well, what's f prime of 1? We can see f prime of 1 is just 2 times 1, or just 2. And we could then tell, if we want to, just for the heck of it, to see f of 1 is equal to x squared, or 1. So the equation of that tangent line would be y minus 1 equals 2 times x minus 1. And using the point 0, 0, the equation of this line here would be same slope. It would just be y equals that slope of 2, 2x. And we can see that those two lines clearly have the same slope. All right, let's see if the square root of 1 minus x squared satisfies the hypotheses of the mean value theorem on the interval -1 to 1. If it does, let's find all the values to satisfy that conclusion on that interval. So, first off, if this is square root of 1 minus x squared, we're going to have to figure out what the domain of this function is. So our domain here is going to tell us that 1 minus x squared has to be greater than or equal to 0, because you can't square root a negative. Or x squared is less than or equal to 1. If x squared is less than or equal to 1, that gives us x is less than or equal to 1, greater than or equal to -1, or it gives us the entire interval that we were talking about here, -1 to 1. And our domain is -1 to 1. There's no discontinuities on here for this. We can include any value in here. And we know that radical functions are continuous on their domain. And thus, this function must be continuous on -1 to 1. And if we were to take its derivative, let's find f prime of x. Well, f prime of x is 1 over 2 root 1 minus x squared times the derivative of 1 minus x squared, which is negative 2x, or negative x over root 1 minus x squared. And we can see that this derivative would exist for all the same values that the original function did, except for when the thing inside this square root equals 0. So this exists, meaning that it is differentiable on the open interval, negative 1 to 1. We just can't include those endpoints, right? Because those endpoints would make the denominator of this 0. And so all we then need to do is figure out what f of 1 minus f of negative 1 over 1 minus negative 1 is. Well, f of 1 is 0, if you plug in 1 to the original function. And f of negative 1 is also 0, so this ends up being 0 over 2, or 0. So our derivative, f prime of c, which is negative c over root 1 minus x squared, 1 minus c squared, must equal 0, somewhere between negative 1 and 1, because the value of our average rate of change was 0. Well, all that would make that true would be c equals 0. And it was guaranteed that there must be a place where that was true by the mean value theorem. If we take a look at f of x equals the absolute value of x, and we want to know if that satisfies the hypotheses of mean value theorem on negative 1 to 1, first thing we have to ask ourselves is f continuous on the interval negative 1 to 1? Well, the answer is yes, the absolute value function is continuous. Absolute value should be continuous always on this domain. So we know that this is a continuous function. We're very familiar with this graph. But the derivative of this function, right, f of x equals absolute value of x, it has a corner at x equals 0, telling us that this function is not differentiable at x equals 0. And we'll just say MVT does not apply. And that's all you got to do for this one. Okay? There's a corner at 0. It's not differentiable at 0. We can't apply the mean value theorem. And let's look at one more here. So this one says, determine if the following function, again, satisfies the hypotheses of the MVT. And if it does, find all values that satisfy the conclusion of it. So the first thing to check is it a continuous function? Well, we know that from negative 1 to 2, x cubed plus 3 always exists, and x squared plus 1 always exists because they're polynomials. But the next thing we'll need to do is we'll need to go in and check and see if this function is continuous at x equals 1. So we're looking at, is f of x continuous at x equals 1? Well, in order to find that out, we need to look at a limit as x approaches 1 from the left of f of x, which ought to be 1 cubed plus 3, or 4, and a limit as x approaches 1 from the right of f of x, which ought to be 1 squared plus 1, which is 2. Well, that's telling us that the limit overall as x approaches 1 of f of x does not exist. And if the limit does not exist, then that tells us that's one of the 3 points of our definition of continuity. The function has to exist, and the limit has to exist. And if the limit doesn't exist, f of x is not continuous at x equals 1. And then we'll say MVT does not apply. And if it's ever not continuous or not differentiable on your interval, you don't need to worry about doing any other work past that. So that's all we're going to look at today for the MVT. Just remember always to check and make sure that the hypotheses of the theorems that you're using have been met. So for the mean value theorem, that means is it continuous and differentiable on the interval given? And then you can just take your derivative and set it equal to the average rate of change. And for Rolle's theorem, you've got to see if it's continuous and differentiable, and also if f of a equals f of b, at which point you can just set your derivative of your function equal to 0 and solve. And should be pretty straightforward.